All right, good morning. Welcome to your science seminar for today. Before we get started, I'd like to ask you to put all away your homework, things like that. Time to give your attention to the speakers. Okay? And also note that I'll be locking the doors here soon when we get started. So if anybody starts pounding on the doors, it's too bad for them. Just let them be. Okay? We have people coming next week who are guests, and we want to show them how we are courteous, attentive audiences. Yes? So when they come as well, you want to put away your homework, you want to give them your attention, you'll want to arrive on time, and stay for the entire seminar. Okay? Because your education depends upon how other people rate this institution, and the people who come to visit us are part of that system. So show them respect, and they will show you respect as well. All right? Okay, we have lots of things coming here in April. Melinda here will be speaking in just a few minutes. But next week we have John Vasili from the UT Tyler, who's going to be talking about smart buildings and how to make all of our buildings here on campus net zero with respect to energy usage, with respect to the grid. Pay into the grid during the day, go out of the grid at night. Can we do that and have a zero energy bill, but for the cost of accessing the grid there? Okay. In 2 weeks we have an alumni coming back to us, John Pearson. He's going to come back and talk about computational chemistry and pharmacology. So all biology majors, chemistry majors, computer science majors will want to come to that talk. Should be really good. And we have another alum coming back from the biology department. We'll be coming back, Nicholas Berggren, who is at UT Medical Branch Department of Pathology. I think he's working on a PhD, MD, or something like that. So he's got lots of stuff to talk about here with exciting things. And then we'll be finishing it out, our semester here at the end of April with statistic talk, math talk. So all the math people will want to come out for that one. So that should be very good as well. Lots of things happening in April. Make sure you have these on your calendar. Right? Yes? Don't want to miss out on any exciting things. So let's see if we can switch over here to Melinda's. There we go. We'll make that big. There we go. So Melinda here will be talking about exciting things. So you want to give her your attention. And after she talks, we'll be having lunch in the corner cafe where you can give her more questions. And we won't be in the Joyce room, but we'll be meeting at that stage area up on the top there. So come and look for us up there, and then you can ask Melinda all the hard questions that you didn't want to ask her while she was up here in front of you. All right, so let's give a warm welcome.
Well, this morning I'm going to be talking on some research that I did this past summer up in Iowa, my home state, at Iowa State University through a program that Ames Lab there in the same city has on Iowa State campus. The Ames Lab Visiting Faculty Program. They invite faculty members from other institutions to work on summer research there on the Iowa State campus with faculty members there. And so I accompanied Dr. DeBoer in this past summer for conducting research there at Iowa State on the Iowa State campus. Now, for a little bit of background, or introduction, that is, to Ames Lab, you can see the front entrance here to Ames Lab, and you've got their logo there up at the top. It's this large letter A with a round red circle, and that's symbolic for their starting point. Ames Lab was founded as part of the Manhattan Project. And so these two faculty members, Dr. Harley Wilhelm and then Dr. Frank Spedding, both were recruited into trying to develop a process of enriching uranium, which could be undertaken on a fast enough level that you could get enough enriched uranium for a nuclear reaction. And so they were actually able to succeed pretty well and donated 1/3 of the enriched uranium to the first nuclear test. And this is the reactor here on the left-hand side being built there on the Iowa State campus. Now that's no longer there in a sense. You can't see it anymore. It's been actually buried underneath the ground and of course stabilized. They do regular testing, so it's not an issue environmentally. But that was the starting point for Ames Lab. Since then, they've moved on to gaining wide recognition for their enrichment of rare earths, as well as refractory metals and other metals. They're one of the leading sources for purified rare earths. Now, the rare earth metals are those not only which can't be found in large quantity in the Earth's crust, but also those which are difficult to separate from their natural ores. And so those include the lanthanides and actinides, just because they're so high mass, they're difficult to separate from their ores. And then there's Iowa State campus. Iowa State actually manages Ames Lab because it started out with faculty from Iowa State who started up the Ames Lab program, and then Iowa State yearly renews their management of the lab. But the campus itself of the university is located in a highly agricultural state, as you may know. Iowa is one of the leading producers of corn here in the U.S. And so it's pretty well known for agriculture. But it's not just known for agriculture. It also has some other firsts that it can claim, as well as notable facilities. You can see there on the left-hand side the first metal water tower built west of the Mississippi River. And then here you can see a virtual reality imaging center. It's called a C6. So it has 6 sides to it, and you can project a virtual image all around the viewer. And then you can also attach sensors, say to your fingertips, to sense touch associated with that environment, as well as a headset to hear sounds associated with it. So true virtual reality in a sense. And then Iowa State campus also has the world's largest tornado simulator on its campus, which is kind of helpful because Iowa's right in the middle of the tornado country there. But to go into the research, our research was basically divided into 2 sections. The first one concerned synthesis of metal matrix composites. Now, these metal matrix composites are composed of a metal, and then you have some other material that's been added in, say a carbide or some ceramic material. You can see here we've got silicon carbide fibers intermeshed in the metal of the copper, making a metal matrix composite up at the top. And then you have down at the bottom silicon carbide particles in aluminum matrix. Now you also have metal alloys, and those are a little bit different because in the case of alloys you have single atoms either substitutionally replacing the atoms of the metal, as you can see on the left-hand side, or interstitially placed between the metal atoms if they're small enough in size. The metal matrix composites that we were creating, or at least trying to create, were based on metals that we had reduced from their metal oxides by means of microwave reduction. Now, these ones that we successfully reduced were iron, nickel, copper, and then bismuth. And then we were reducing them in the presence of carbon. So this carbon was in the form of carbon nanotubes. And so we were trying to make these carbon nanotube metal matrix composites. To give a bit of a background on some of these metals, you can see here that these ones circled in blue are transition metals because they're in this D block of elements between groups 3B and then the 2B there you can see. And then there's also bismuth, and that's a semi-metal. So it's a little bit different. But the transition metals, according to the UPAC definition, are elements whose atom has a partially filled d subshell, or which can give rise to cations with an incomplete d subshell. And so that's basically saying that you have these atoms which don't have all these d shell electrons filled in. So you don't have all 10. Instead, you might have just 5 or just a few. And that can change their properties, their bonding capabilities. Now, as transition metals, they do undergo metallic bonding. And you can see an example of that up the top. You've got these positive nuclei throughout the material, the metal nuclei, and then the electrons are just moving about throughout the whole as a sea of electrons. But as transition metals, these materials can also undergo ligand bonding, and that's shown here at the bottom. You have a metal atom with an empty orbital on it, and then you have another atom which approaches with an extra set of electrons. So those electrons can be donated by that atom. Say it might be a phosphorus atom, and it donates an extra electron pair to the metal atom, and that can bind to create a coordination covalent bond. So it's a little bit different from pure covalent in that all the electrons are coming from the one atom. They're not being donated by both. And then as metals, these transition metals are also conductive. So you can have electron current taking place. And then they show many oxidation states. And that's partially just because you have different states that are stable for the amount of electrons that you have in the orbitals. In the case of this periodic table again, you can see that there are 10 columns here among the transition metals, and so you've got 10 electrons in the d orbitals. And so there's a stable state at 5 electrons, there's also a stable state at 10, and you can also have a stable state at 4 if you take an extra electron from the s orbitals over there. And so there's just more variety available to these transition metals in oxidation states. Now, the specific metals that we were looking at were nickel, bismuth, and iron, and then there's also copper as well. But the nickel, bismuth, and iron all have melting points below 1,540 degrees C, and that's quite a bit lower than the temperatures that blast furnaces reach. Blast furnaces provide the standard method for reducing these metals. You can say, take the example of iron and purifying it and refining it from iron into steel with a blast furnace. Now those blast furnaces are highly inefficient because you have a lot of heat that escapes and is lost, and so that energy is not being used to reduce the metal oxides. In this case, we were looking at the first summer, this is back in 2013, reducing these metal oxides to their pure metals with the maximum possible energy efficiency. And that was by the microwave reduction, which I'll go into a little bit more in a moment. The other component of these metal matrix composites were the nanotubes. You have two types principally, the single-walled carbon nanotubes and then the multi-walled. And they differ in two main characteristics. One is the diameter of the nanotubes. The single-walled are only 0.5 to 1.5 nanometers in diameter, while the multi-walled are up to 50 times that, going up to 50 nanometers in diameter. And then the other characteristic, which is pretty obvious, is that you've got, for the single-walled, only a single cylinder of carbon atoms, whereas for the multi-walled you have multiple layers there, which gives rise to their name. And then you can, based on the structure of these nanotubes, you can see they're arranged in hexagonal rings, which are all bound together into a tube. That gives them very high tensile strength. They can be spun together into fibers and threads, and those are one of the strongest known for fibers and threads. But here I'll illustrate our basic procedure for making these metal matrix composites. We started out with a quartz crucible, which we used instead of the standard glassware because it's more, has a higher thermal stability. It's not going to be as likely to fracture with a sudden change in temperature. And then we added nanotubes to that and about half filled it, and then added oxide on top. And then we just placed that in a standard microwave oven and heated it for 0.5 to 2 minutes. And in that time period, you would get plasma forming often that you would see, and then a fair amount of noise associated with that. But at the end, we would get this metallic product that formed. Especially with the iron, you could get a nice, clear conglomerate of metal. And then we'd take that and prepare it in various ways to analyze it by scanning electron microscopy, or SEM, X-ray diffraction, or XRD, and then microhardness testing as well. Now, the first summer 2013, was when we focused on making the microwave reduction products. This second summer, summer 2014, or just the last summer, we focused more on the analysis here. Here are some SEM images of the bismuth-3, the nickel-2, and then the iron-3 reduction products. And I could tell in looking at these, after running also elemental analysis, that there's pure metal here that's been formed. And that you can tell, especially when you look at backscatter, because the metal shows up really bright, whereas you have this dark background for the mounting material, which is mostly carbon. So it shows the difference in density of the atomic character. Here I also brought a blown-up image of this sample on the far right, the iron-3, and I was looking at here these dark areas that I saw in apparent oxide material. And those I also analyzed under SEM to check what elements were present, but I couldn't really get a good reading. I thought it might be carbon, the carbon nanotubes conglomerating together, but I didn't really get a good carbon reading. And we also earlier checked these by Raman spectroscopy, which basically looks at the covalent bonds in the material, and we couldn't get a good carbon-carbon bond read for these dark areas. And so with a little more thought, it seems likely that these dark areas, dark patches, are actually bubbles in the material. If you consider what's going on, it's a reduction process, and so the iron oxide is being reduced by metal, and the oxygen is binding to the carbon and creating carbon dioxide. And so you'd have this outgassing of carbon dioxide forming these bubbles in the material. Now onto some of the analysis here. Also in microhardness testing. The microhardness testing basically works by having this indenter come down, and it had a very sharp tip made out of a diamond fragment. And that was also shaped in a diamond pattern. And this would be lowered down into the surface of the material and then raised up. And then you would measure the distances between the points. And the computer software would take those distances and calculate the hardness based on the known weight applied to the indenter. And so you can see some of the samples that I ran hardness testing on. Probably, I think those are copper samples there up at the top, and then maybe some bismuth as well. But the machine is actually pretty small. It's just about the size of an old PC desktop computer. Here are the actual measurements that I obtained. These were Vickers hardness testing. And so it's based on the pattern of the indent. It's the diamond pattern. So it's measured in HV, hardness Vickers. But the first column shows the measured hardnesses, and then you have the reference hardnesses in literature, and then hardnesses reported for different metal matrix composites. So when I measured the bismuth hardness, you can see that its hardness closely matched the reference hardness for the pure metal, and so it looked like we were indeed getting just pure metal in that reduction. The copper, though, surpassed the low-end hardness of 38. That's for the pure metal. And it reached more the metal matrix composite hardness of 66.1. And that was reported by a previous graduate student who actually began this research into these metal matrix composites. The same occurred with the copper 2. You're again getting around 66.1 HV. When I looked at the iron 3 and the nickel 2, they also passed the hardnesses for the pure metal. However, the problem was it was difficult to find in literature examples of the hardness reported for a carbon nanotube metal matrix composite. And so I compared with the closest ones I could find with other materials, tungsten carbide in this case, and silicon carbide, and it is getting up closer to that range. So it's a little bit less certain there just because I don't have a good reference, but it doesn't really seem to be just the pure metal. Now this is a X-ray diffraction spectrum of the bismuth reduction, and you can see that I matched it to a reference spectrum in a database and found that I'm getting consistent peaks for the pure metal bismuth. The iron was a little bit more difficult just because sample preparation was more difficult. I had only small fragments of the metal, and iron is considerably harder than bismuth, as you may well know. So what I was doing to prepare the sample was to grind it with a file into small fine powder so that I could get a good reading. Basically, XRD works by taking an X-ray beam and directing it on a sample, and the X-rays interact with the atoms in that material, and they are deflected in a specific pattern, which indicates the crystal structure that the material has. And that crystal structure can be matched up to specific metals and their phases. And so in this case, I had to grind the material into a powder, and it was very difficult with this harder metal to do that. And so the readout just wasn't as good. But it does still look like I was matching the peaks to pure metal peaks, as you can see, just in two different phases there. Here also is the nickel spectrum for XRD, and that again is showing matching for the pure metal peaks. And so I'm definitely seeing that there's pure metal in these samples. The summary of all this is shown in this table here. You can see that for the copper, the iron, the nickel, and the bismuth, pure metal was found in the samples. And then also for the copper, the microhardness testing indicated that there was indeed a metal matrix composite that was being formed. The iron, the nickel, and the bismuth were a little bit more difficult to assess for metal matrix composites, just because there wasn't good reference data to compare to. But so that part of the research was a little bit more open at the end. But at this point, we had to transition on to another area of research that our mentor was encouraging us to pursue. And that sort of branched off of the first summer's research in 2013, which this here was finishing up. And this second area was trying to develop these polymer matrix composites. So again, another type of composite. But in this case, you have a polymer that is acting as the matrix, into which you're adding this other filler material. And so here we were working with nanorods as the filler material. These are aluminum nitride, and we were adding them to a BSI in abbreviated form. It's a bisphenol E polymer, and putting them into that matrix. These were created for the purpose of making structural capacitors. The structural capacitor differs from a standard capacitor in that it's incorporated into a circuit board that it's serving as a component for. rather than sitting on the top of the board. And so in this way, you lower the risk of mechanical failure just by having it more protected within the board itself. And then also there's the fact that you're reducing the size, or that is the volume taken up by the capacitor, just because it's integrated into the board. And so you can make more compact electronics. The polymerization process for these composites started with first mixing the materials together, and that was done by sonication. We started out with the monomer material, which is basically the plastic in liquid form. It's not been polymerized. You've got a bunch of small molecules. And then we added the filler material, the nanorods, and to that we also added the catalyst for the polymerization. And so we would mix these up with sonication, which functions by emitting high-frequency sound into the liquid material. And that actually works to stir the material around. And you'll see lots of little bubbles rising to the surface just because things are being stirred so well. And because of that, those gases that we saw in the material, we also, as a second step, we went on to degassing in a vacuum oven. And so we basically placed the liquids in this vacuum oven and just evacuated the chamber without heating it to allow that gas to escape from the liquid. After that, we poured the liquids with the filler material in them into rubber molds and placed them in a temperature-controlled oven, an isothermal temperature-controlled oven. And this heated the samples for several hours at different temperatures, first at a lower temperature and then at a high temperature, and that effectively cured the sample, or did what's called curing. In curing the sample, it basically just solidified it, so it polymerized the monomers into the full chain. After they were polymerized, we took the samples out, removed them from the rubber molds, and then cut them into thin 1 millimeter thick strips. These we could then analyze by the different instrumentation. The first of these was thermogravimetric analysis, abbreviated TGA. And that works by taking a sample that's placed in a metal pan, and that sample is grabbed by a thin metal hook over here that automatically comes over, lifts this pan up, brings it over, and then lowers it down into the furnace. And then the furnace comes up and the sample is enclosed. There's also a thermocouple there that you can see, and that's measuring the temperature change, because this sample is going to be heated to burn off the material over a range of temperature. And the hook also is attached to a mass measuring component, and that's going to measure the change in mass as the sample's heated and burned away. And so you're looking at the change in mass over a change in temperature. Here you can see the weight percent change for one of our sample sets over this temperature range up to 540 degrees C. And you can see that there's a major drop in mass around 455 degrees C. That's for the one weight percent. But if you look back at the green line, the pure polymer itself is burning away at 445 degrees C, or 446. So that's about 10 degrees lower. So you can see that the decomposition temperature for these samples was raised by the addition of these nanorods. And those 7-minute nanorods were made by microwaving carbon nanotubes in a microwave oven for 7 minutes. That's their name. And they had a thicker diameter than these other 2-minute nanorods, which were only microwaved for 2 minutes. Here is a different type of chart that's showing how the mass changed at different temperatures. This is isothermal, and so once the instrument detected a change of mass at a certain temperature, it held that temperature constant until the change of mass ceased. And so the sample stopped burning at that temperature. And then it went on to ramp up the temperature further until it reached another burning point. And so you can see that the sample is burning away at two different temperatures, it looks like. One at about, let's see, 448 degrees C, and then another at 511 degrees C or so. And that might be because you have two different types of polymers in this, one cross-linked and one not, and so those would have different burning points. These images are also scanning electron microscopy images, as you saw before for the first research segment. And they're looking at the surfaces of the polymer here at the bottom, and then at the nanorods up on top. These nanorods, as I mentioned, were formed by microwaving nanotubes. And that was something that we sort of discovered accidentally in the process of reducing the metal oxides in the presence of nanotubes in the microwave oven. We just looked at the nanotubes themselves one day with the scanning electron microscope and found these nanorods in there. And so these are aluminum nitride, and you can see they have growth rings on them. And if you look carefully, that's sort of hexagonal shape because the aluminum nitride itself takes on a hexagonal morphology. These surfaces show the different weight percents that we prepared for the polymer. That is, weight percent of nanorod in the polymer material. And so we've got 1.0 on the far left, 0.5 weight percent of nanorods in the middle, and then 0.2 on the right. And you can tell that these weight percents, which we measured out before we polymerized the material, did still hold true for the solidified polymer. We've got a lot of rough material in there, that's the nanorods, for the 1.0, and much less for the 0.2. And you can also tell from this that they're pretty evenly dispersed. In the 1.0, it's pretty much rough all over the surface. It's not clumping together in certain areas. And so that's good because we want the filler material to be evenly dispersed in the polymer. Now another test we did was dynamic mechanical analysis, abbreviated DMA, and that stretches the sample over a range of temperature to see how much force it can withstand before yielding. This is done to measure the glass transition temperature, or the point at which the sample changes from a stiff state to a more rubbery state. When you take the plot of the strength modulus versus the temperature for a sample and stretch the sample over this range of temperature, you'll see a sudden point where the strength suddenly drops. That's where it's yielding, and that's the glass transition temperature. For the actual data here, these are the Tubinet nanorod samples. So they had the smaller diameter nanorods in them. And you can see that we had, for the pure polymer of that set, a glass transition temperature of 293 degrees C. But for the 0.28%, that dropped down to 284 degrees C. So almost a 10-degree drop in temperature for the glass transition temperature. The other composites, the 0.5 and the 1.0, didn't show as much of a change, and I'll get into that a little bit more in a moment. But just note for now that there's not as much change for those composites. For the 7-minute nanorod samples, the data was a little bit less interesting. The pure BSI, or the pure polymer for that set, had a glass transition temperature at 278 degrees C, just a difference in sample preparation, unavoidable difference. And then the 0.2 prepared with the same pure polymer had a TG of 276, and so it's only dropped by 2 degrees C about. And then the 0.5 and the 1.0 are just about the same. And so these 7-minute composites didn't show a distinct character change from the pure polymer. One last method for analyzing these composites was thermomechanical analysis, and that's abbreviated TMA. In that, you take a cubic section of polymer material, and you place it under this glass probe, which presses down with a certain force. And then the furnace is brought down over the sample, and a thermocouple measures change in temperature as the probe presses against the sample, and the temperature is ramped up over a range. And so effectually what you're doing is measuring the dimension change of the sample, or the change in volume of the sample, with a rise in temperature. Here you can see representative graphs. On the left-hand side, you're actually passing the melting point. You can see that there's a sudden volume change, and that's indicative that the sample is melting all together. And here on the right-hand side, you can see where you're passing the glass transition temperature, the TG. And so the slope is just increasing in angle, or that is, the volume's suddenly increasing more as the temperature goes up. So it's passed into rubbery phase at that point. Here's some of our data for the 2-minute nanorod composites. And there you can see that the pure polymer itself showed a coefficient of thermal expansion, which measures fractional change in volume over temperature, of 69.78, whereas the 0.28% showed about a degree higher. And then you have, for the 1.0, 44.0. And that, I think, is just an outlier data line, because you can see that the graph itself, you have this downward slope and then upward. And so that may be due to the sample slipping beneath the probe, because that's not the sort of graph that you should get. And so this data for the 2-minute set was a little bit more unreliable, just because of that deviance in the data for the 1.08%. For the 7-minute nanorod composites, you've got clearer lines here. And for the pure polymer, there is a coefficient of thermal expansion at 69.78. For the 0.28%, it's 51.83. So it's dropped down a good 17 degrees, not 17, 17 units for the coefficient of thermal expansion. And then the 0.5 and the 1.0 show lesser drops for the composites. And so again, we're seeing that the 0.28% is showing distinct change from the pure polymer. Now, you've heard glass transition temperature mentioned multiple times here in the course of the presentation. And that may be a slightly unfamiliar term, but it's very useful and important when looking at polymers. Here's some research on the left-hand side where you can see plastic components developed, say for a medical implant. And those have a glass transition temperature right about at body temperature. And so you could heat them to have them collapse and then insert them during surgery, and then they would expand again into rigid form to take on their function as a medical implant. And then here on the right-hand side, you can see some cell phones. But right there, the focus is just the cell phone cover. There you have some more rubbery type plastics on the surface. And those are rubbery because they've got a glass transition temperature that is approached at room temperature. And so you're getting more grip on them because they're in that more rubbery state. So that illustrates the usefulness in both medical research and then also just in day-to-day items like cell phones of the glass transition temperature. But this summarizes the measurements performed on the different instrumentation for these composites. On the left-hand side, you see the measurements with the TMA for the coefficient of thermal expansion, and that showed the greatest drop in the coefficient of thermal expansion for the 0.2 weight percent. Again, the first 2-minute set had that deviating sample in there, so it's less reliable data. And then on the right-hand side, you can see the DMA measurements, or the dynamic mechanical analysis, and those measured the glass transition temperature. And there, again, you're seeing that the 0.28% is showing the greatest drop in glass transition temperature. Now, this marked difference between the low weight percent and the high weight percent occurs because when you get a high weight percent of filler material added to a polymer composite, the filler material tends to aggregate in clumps, and so it functions less effectually as a composite material. And so we would expect that the low weight percent composites show better properties, as we were indeed seeing. To summarize, the first segment of research worked on the development of metal matrix composites. And so we were able to reduce certain metals, but not others, including aluminum, calcium, and some of the other metals, metal oxides, with high reduction potentials, or highly positive reduction potentials. And that was found out mainly through the first year of research, and then we went on to analyze our samples the second year, this past summer. And then we also found that few of the metals, besides copper, are showing solubility for the nanotubes. As illustrated before, only the copper had a distinct metal matrix composite that we found in it, and we weren't really detecting carbon in these other samples as well. That was the main indicator here that we didn't have metal matrix composites. And so, as we also realized in looking at the data, these other metals just don't have high solubility for carbon, but copper does have better solubility. So it looks like the better option here in making these composites, if you're wanting to use the microwave route, is to take pure reduced metal in particle form and add the nanotubes directly to that and mix it all together, and just work on sintering the metal and the nanotubes with the microwave heating. Because the actual reduction of the metal doesn't work in certain cases where the reduction potential can't be overcome, and other metals just aren't showing good solubility for the nanotubes. With the polymer matrix composite research, we found in looking at the scanning electron microscopy images that the nanorods, I'm sorry, getting mixed up between these two research segments. The nanorods were getting readily dispersed in the BSI polymer, as you could see by the roughness in the surfaces, and these were also evenly distributing throughout the polymer, because we weren't seeing clumps of nanorods in certain areas of the surface. And then also with the analysis, we could see that the glass transition temperature was markedly dropping for the 0.28% nanorod composites. And then also we looked at the coefficient of thermal expansion, and that was a little bit less clear just because we had that outlier data, but it looks like the nanorod composites, the 0.2 nanorod composite, did show the most distinct change in coefficient of thermal expansion. We weren't able to get into the measurement of electrical properties for these composites because by that time the summer research finished, or the summer term for the research finished. But now I would like to acknowledge, in concluding, the funding that we had from the Department of Energy, and then the Ames Lab visiting faculty program through which we did this summer research at Iowa State. And then Dr. Sami Madbouli, who hosted us in his research group there in his polymer composites labs. And then the different faculty and staff there who we worked with in getting training on instrumentation, and just talking with to discuss how the research was going forward. And then also my brother Derek Hoyt, who we collaborated with long distance in transitioning from the first summer of research to this second summer of research in analyzing these metal matrix composites further. But with that, I'll conclude and open it up to any questions that you might have.
Questions for our speaker today?
Yes?
When you were doing the microwave heating with the microwave ovens, did you monitor the energy or the power used during that the last time? 2 minutes, 1.5 minutes?
These were standard microwave ovens, and I believe, if I remember correctly, it was 2.45 megahertz or gigahertz? Gigahertz. And so it was set at that max power standardly for all the reductions. Yeah?
Can I just follow up on his question? So the power was something like 1.3, 1.5 kilowatts, but you can't change it with the microwave. All you can do is change like the amount of time, or 50% power is off 50% of the time, on 50% of the time. There's no ability to change that. If you used probably the same one that we used
We did,
a year ago.
yeah. The only way you can really change power in a sense is if you modify the microwave oven itself, which we did do in a couple experiments by drilling some holes in it to try to add in a different atmosphere, say of argon or carbon dioxide, and that just let the microwaves, well, not escape, but it interrupted their bouncing around in the chamber, and it just less effectively heated the sample when we did that. Yes?
And when you were using these standard microwaves and you were creating plasmas, did you see some major arcing?
There was some that we could see. We could see some sparking, and we did see some arcing apparently appearing in some of the plasmas. But mainly it was just this cone of bright light of the plasma itself, and sometimes that would rise up to the ceiling of the microwave oven and spread over the ceiling for certain reactions.
Any questions from Melinda?
Yeah.
I have a question. If you go back to your slides, the DMA graphs you have. Yes. So I see you have for different weight percents nanorods, but what's those? There are 4 lines, blue lines and 4 green lines. What's the green versus the blue?
Oh yes, I forgot to mention that. The green is the storage modulus versus the temperature, and then the blue is the derivative of that. So you're looking at how the slope changes.
I was going to say the blue, if it's a different material, it's a very strange
No.
glass transition.
No.
property.
That was just to pinpoint the exact glass transition temperature.
Well, after doing all this work, Melinda applied to graduate schools and she accepted all kinds of places. But she has decided that she's going to continue her graduate study in material science engineering at Iowa State. Yes, is that correct? Yep, and they'll pay her a big amount of money to do that, because if you graduate with a bachelor's degree in chemistry, you'll get paid to go to graduate school. So all those who don't have their degree in chemistry, go back down there to the registrar's office and change it so that you have a degree that is good when you get out, you get paid to go to graduate school. We will continue our discussion some more on how you can become a chemistry major over at the Corner Cafe. So see you there.